Hi guys. So today we're going to transition from looking just at rational expressions to actually looking at rational equations. So instead of just simplifying or rewriting an expression, we're actually going to solve for an answer for x now. There's really two different methods we can use. One of them is cross-multiplying. One of them is using the least common denominator. So if we're cross-multiplying, it's exactly like it sounds. We'll multiply across one diagonal. We'll multiply across the other diagonal and set them equal to each other. So I end up with 9x plus 9 equals 12x plus 15. And then it's a simple equation at that point. Now, cross-multiplying works best really when you have something in this form where you just have a fraction equal to another fraction. All right, so that's what I end up. And again, when it comes to equations in general, but especially with rationals, we need to check for extraneous solutions, particularly if it's a value that would have been an excluded value on an expression. So in this case, -2 does work, so that is an actual value. All right, so now let's go on to least common denominator. So you've really got two different ways that you can work this out, depending on what's easier for you. One is you can multiply your entire expression by the least common denominator and then simplify your fractions to clear them that way. The other option is you can get that common denominator and then just solve the numerators. So that's typically the way that I use it, just because if the denominators are the same, let's say this is x, well, let's use a number. Let's say this is 5, and this is 5, and this is x, and this is 7. If the denominators are the same, then all we need to check is the numerators. Doesn't matter what it is, or if we're adding multiple fractions to it. Because when you add and subtract fractions, you don't change the denominator. You combine them together once they have the same denominator. So then all you really need to solve is the numerator. So that's the way that I typically work it out. So this common denominator here is going to be 4x. So I need to multiply by 4, by x, and by 4. So that gives me 20 over 4x plus 7x over 4x equals -36 over 4x. Again, since the denominators are the same, at this point I can just solve the numerators. So I get 7x equals -56, x equals -8. Again, the other option, like I said, is you can multiply the entire function by the common denominator to clear it out. So if I multiply everything by that denominator of 4x, well, on the left, those x's would cancel. I'd get 20. Over here on the right, I'd get 7x. Over here on the left, I would get -36. So either way you do it, you still arrive at the same equation. Just a matter of which way kind of makes more sense or which way is easiest for you. Again, check to make sure that answer is not extraneous. In this case, it's not. And we have our solution. All right, so let's go ahead and go to the next one. Now again, you guys, you can use a combination of these two methods. So if you wanted, like on this next example, if you wanted to just combine these two with a common denominator and then cross multiply, you could do that. I'm going to go ahead and get that common denominator though, just because I think it's a little bit simpler. X squared minus 9 factors into x plus 3x minus 3. So that is our common denominator. That means that the right fraction just needs the x minus 3. The left fraction needs the x plus 3. The middle fraction's already good. So now I have 6 times x plus 3 equals x squared minus 4x times x minus 3. And then we just have, once we distribute and combine like terms, we have a quadratic equation. So then at this point, we'll set it equal to 0. Combine our like terms. And this time we have a GCF. So what you'll notice is we can, instead of factoring out that GCF, since we're dealing with an equation, we can just divide every term by that GCF. So I can take everything and divide it by 2. So I'm going to go ahead and do that. So that leaves me with 2x squared plus 3x minus 9, which I can factor. Now, whatever factoring method you want to use, if you want to split the middle, do your grouping, that's fine. But I think when one of those first or last numbers is prime, it's a little bit easier just to fill in your factors. So what I mean by that, we know those first two numbers have to multiply to be 2x squared, because whenever I FOIL it out, that's just how it's going to work out. Well, the only numbers that multiply to 2x squared are 2x and x. I know my last numbers have to multiply to -9, which means they're either 1 and 9 or they're 3 and 3. One of them is going to be positive and one of them is going to be negative. To figure out which option we pick, what we need to do is check those middle terms. Those middle terms are going to add to that 3x. So let's say I tried 9 and 1. One could be positive and one could be negative, but it doesn't matter. I'm not going to end up with 3. Even if I flip it, I'm not going to end up with 3. So I can try 3 and 3. Well, then if I check those, I get 6x and 3x. Well, again, one of those 3's has to be negative in order to multiply to be a negative 9. And because I want it to be 3x, I want this to be negative. The other way you could do this, again, if you're filling in those factors, if we test those middles, the normal way we start this out, if we multiply a times c, what multiplies to a negative 18 and adds to 3, those numbers are 6 and negative 3. Well, if you check those middle branches there, or the inside and the outside, one of them is negative 3 and one of them 6. So it's the same thing. We're just getting there a little bit of a different way. But again, there's nothing wrong with split the middle and splitting the middle and doing your grouping. That also works. So then from this point, we find our solutions. And you'll notice now, if x equals negative 3, if I were to go back to my original equation and plug that in, I'm going to be dividing by 0 over here, which we cannot do. So that is an extraneous solution. So the only value I have is 3/2. All right, if you feel pretty comfortable, pause the video, try the next one. All right, on this one, x squared minus 1 factors into x plus 1, x minus 1. So that means that's my common denominator. So that means that the middle fraction needs to get multiplied by that x squared minus 1, because remember, any whole number is just divided by 1. The left fraction is going to need the x plus 1. So this gives me 7 times x plus 1 minus 5 times x squared minus 1 is equal to 6. Denominators we don't need to worry about because, again, those denominators are now the same. So 7x plus 7 minus 5x squared plus 5 equals 6. We'll set it equal to 0. And then again, I need a factor. I'm going to do this the same way, where I'm going to fill in my parentheses, because 5 is a prime number. So if 5 is a prime number, well, those two things, that has to be 5x and x. My other two are going to multiply to negative 6. I also know, again, if I do this with a split the middle, I need something that multiplies to negative 30 and adds to negative 7. That's a negative 10 and 3. That's what those other two branches are going to multiply. One of them is going to multiply to negative 2. The other is going to multiply to 3. So that means that the ones that are on there, again, those last two are multiples of negative 6. And then when I multiply those out, I end up with negative 7x. From there, I actually find my solutions. And I get x equals negative 3/5 and x equals 2. All right, so that's just basic equation solving. We're going to look now at a couple other things, like inverses, inequalities, and word problems. So inverses we've been doing kind of since the beginning of the year. So remember, in order to find an inverse, you switch x and y. So to the inverse of this equation, I would do x equals 3y minus 2 over y plus 7. So in order to get this solve for y, I need to go ahead and get these y's together and separate it. So what I'm going to do is I'm going to go ahead and multiply both sides by y plus 7. That way I can get rid of that fraction. All right, now I'm going to go ahead and multiply and distribute on this left side. And you'll notice now there's 4 terms in this whole equation. What I want is every term that has a y to be on one side and every term that doesn't have a y to be on the other side. So I'm going to rewrite this way. Again, all I really did was flip the places of those two in the equation. The reason I did that now is both terms on the left have a y in them, which means they have a GCF of y that can get factored out. And once it's factored out, that means it's y times x minus 3. So to get y by itself, I can divide by x minus 3. So the inverse of this equation is right here. Now, depending on how you work this out, you may have gotten a similar answer that's slightly different, but it is still the same equation. And that answer is 7x plus 2 over 3 minus x. Those are equivalent statements. Okay, they're the same exact function. The only difference is we basically took this equation and multiplied everything by -1. It's still the exact same equation, and depending on how you worked this out is how it would look. Either of those answers is okay, though. All right, so now let's look at inequalities. So inequalities, we're going to work these out very similar to the way we did quadratic inequalities, where we made that chart, we plotted our possible x-intercepts, we found where our graph was positive and negative. The only difference with rational functions is that your graph can change from positive to negative at an x-intercept, but your graph can also change from positive to negative at a vertical asymptote. So when we make our number line, we're not just going to include the x-intercept, which in this case is 2/3. We're also going to include the vertical asymptote, which is -7. So I'm going to mark both of those points. And then just like we did with quadratics, I'm going to pick a test point in each region. This is also what we did when we were graphing if we needed to check to see if our graph was positive or negative. So if I pick some value over here in this region, like a -10, if I plug in a -10 to the top here, that would give me a negative number. If I plug in a -10 to the bottom, that would give me a negative number. And a negative divided by negative overall in this region is positive. Then I pick a test point in the in-between, like 0. Well, if I plug in 0, that's going to be a negative divided by a positive, which overall makes that section negative. Pick my far right point, like 1. All right, 3 times 1 minus 2 is positive. 1 plus 7 is positive, and a positive divided by a positive is positive. Again, you can also use the information that you know from these graphs. The fact that, there aren't any squared factors, so I'm going to alternate those signs. That's another thing that you can use. But again, it's good to pick at least a couple test points just to make sure you're going in the right direction. So once your chart's filled in, you use it to answer the original question. So the original question was when the rational function was less than or equal to 0. Well, that is the negative region. Now, what makes these a little bit harder than quadratic inequalities, we need to consider the difference between a vertical asymptote and an x-intercept. The vertical asymptote here at -7 is never a point you can actually touch. So even though this is or equal to, and we would typically use brackets, we can only use a bracket on the 2/3 because 2/3 actually is an x-intercept. It actually is a value where your function can equal 0. Since -7 is a vertical asymptote, your graph actually can't equal 0 at that point. It just gets very, very close to, it's just going to keep getting really, really close to -7. We can't actually reach it because it's undefined at that point. So you're going to have a parenthesis on one side and a bracket on the other. So it is important to consider the difference between a vertical asymptote and the x-intercept in these cases. Now, if it's not or equal to, it won't matter. You'll always use parentheses. But in a case where it is equal to, that is a consideration to keep in mind. All right, on this next one, very similar, but we have one additional step. Just like with quadratics, if we're testing positive versus negative, we need to consider this function in relation to 0. It's really hard to tell if it's going to be above or below -2. All right, we can't really use x-intercepts and vertical asymptotes to help us with those points in between. So our first step here is going to be to set this function equal to 0. So I'm going to go ahead and add 2. But now, in order to find our vertical asymptote or x-intercept, I need to go ahead and combine these together into one fraction. That means I'm going to need to get that common denominator of x plus 2. So now I have x minus 3 plus 2x plus 4, which I can simplify to 3x plus 1 over x plus 2. So now that's the function that I'm going to use to test my points and make my sign chart. Well, the x-intercept here is a -1/3. The vertical asymptote is -2. And then from here, pick your test points in each region. Something to the left of -2, if I pick a -10, that's going to be a negative over a negative, which is positive. If I pick a -1, that would be a negative over a positive, which is negative. And if I pick 0, that's going to be overall positive. Again, go back to the original. We want to know where it's greater than 0. It's not or equal to, so we're going to use parentheses no matter what. and we're looking for the positive regions. So negative infinity to negative 2 and negative 1/3 to infinity. All right, so the last thing that we're going to look at are some word problems involving rational functions. This first one's a little bit harder, and I think it's because it's worded a little bit of a difficult way. But we'll go ahead and go through this, and then we're going to look at some very typical rational functions involving rates. All right, so it says sterling silver is an alloy composed of 92.5% silver and 7.5% copper by weight. You have 15 ounces of 800 grade silver, which is 80% silver and 20% copper. How much pure silver should you mix with the 800 grade silver to make sterling silver? So what we have is we have this mixture, okay, that is currently, we have 15 ounces of a solution that's 80% silver and 20% copper. We are trying to make that solution have 92.5% silver and 7.5% copper. In order to do that, currently there's too much copper in that solution. So we need to add silver in order to change it. We're not going to change the amount of copper in there. So what we need to consider basically is part to whole. All right, so if we look at that 800 grade silver, the part that we have, okay, the weight of the copper over the total weight, that's going to be one of our parts to our whole. If we're talking about it in terms of the copper, okay, then what we want that to end up being is 7.5%, because that's what we need our solution to be. The reason I'm doing this in terms of copper is because copper is not changing. We're not adding any more copper to our solution. What we are adding is silver. So the total weight is going to be composed of the amount of liquid, or the amount of silver, or the amount of 800 grade, I shouldn't say silver, just the amount of 800 grade that we already have, which is 15 ounces. Then we're going to add however much silver we need to get the consistency we need. That's going to be the total weight of our product. So X here is standing for the ounces of pure silver to add. And that would be our total weight. Well, again, the total weight here, we're not changing the amount of copper. The amount of copper we currently have is 15 ounces, and of that 15 ounces, 20% is copper. So 15 times 0.2 is the actual amount of copper we have in our product. So we're going to keep adding silver until that percentage is 7.5%, or 0.075. So that's our rational function. So these word problems, once you get the function set up, they're pretty easy to solve. A lot of them are just simple cross-multiplying or simple common denominators, but actually getting the equation set up can be a little bit difficult. So we can go ahead and finish work. So if I cross-multiply, 15 times 0.2 is just 3. 0.075 times 15 would be 1.125. We'll get x by itself. And I get 25 ounces. Now, there are other ways that you can work this out. Some of you I know can find some ways without using rational functions, but I do want to just show kind of how to set this up as a rational function in order to get your answer. Now, more of the typical word problems we're going to look at are these rate and time questions. So we looked at kind of the basic example in class of, Joe paints the house in 3 hours and Sam paints the house in 5 hours, how long for them to paint it together. Similar concept that we're going to use on these. Whenever we're talking about questions involving a rate or how long it takes, we need to remember that distance is rate times time. And the amount of work that you're doing, okay, it's going to be whatever your rate is to do it times the time you actually take. So in this case, it's telling us that Harry takes 7 more hours to paint a kitchen than it takes Sally for the same job. Together they complete the job in 12 hours. So that means that their combined rate is they can paint one kitchen in 12 hours. Individually, let's look at what they have. So individually, it takes Harry 7 hours more. So he can paint one kitchen in 7 hours plus Sally's rate. Sally, we don't know her rate, but again, one kitchen in her rate. So that's Harry and that's Sally. So again, what we're setting up here, that rate is the amount of work they do over the time it takes to do it. We don't know what those rates are yet, but we know that combined, those rates will be that 1 over 12, because they can do one kitchen in 12 hours. At this point, again, it's a basic rational function. So I'd multiply the left fraction by x, the right fraction by 7 plus x, and then I can, actually what I'm going to do is just combine those two together. So that's going to be 7 plus 2x over my common denominator. And then I'm going to go ahead and cross multiply. So I end up with 7x plus x squared equals 84 plus 24x. At this point, we'll set it equal to 0. This does factor. And I'm trying to think of my answer before I actually do my math. So that is going to be x squared minus 17x. So those numbers are going to be 21 and 4. Once you know your factors, you get two possible answers, 21 and negative 4. Well, negative 4 doesn't make any sense for the problem. It's not going to take them a negative amount of time to get this job done. So x, 21, that's the amount of time it takes Sally to get this one job done. So it takes Sally 21 hours, which means that it's going to take Harry 21 plus 7, or 28 hours. All right, so we'll look at another one that involves these rates and times. So this one, again, instead of looking at work, we're going to look at distance. So a car travels 500 miles in the same time that a train travels 300 miles. The speed of the car is 30 miles per hour faster than the speed of the train. So again, distance is equal to rate times time. In this case, we know that the times are equivalent. We know that the amount of time it takes one car to get 500 takes the same amount of time for that train to travel 300. So distance divided by rate is going to be those times. We don't know what the rate is, but we know information about the rate, which is why we're going to use it in our expression. So the car is 500 miles over some rate. We don't know what that rate is, but we know that it's 30 miles per hour faster than the train. We know that the car or the train is traveling 300 miles per hour for whatever that rate is. We know that they're equal. Again, distance divided by rate gives us time, and those times are equal. It takes them the same amount of time to do those things. At that point, your rational function is set up, and then we just need to solve from there. So I get 9,000 plus 300x equals 500x. So I get that x equals 45. And again, in this case, x is the slower speed, which is the speed of the train. So the train is traveling 45 miles per hour, and the car is traveling 30 miles per hour faster, which is 75 miles per hour. All right, the last thing that we're going to look at is just a question a lot of you kind of asked once we got into rational functions, and that is determining where a function crosses the horizontal asymptote. And I realized this question wasn't actually finished. Okay, so in order to solve this algebraically, every equation that we solve is an intersection question. So it's the same thing here. The first thing to determine is what the horizontal asymptote is. Well, equal degree, so I divide the leading coefficients, which in this case is 2 divided by 1. So I want to know where this crosses the line y equals 2. So all I do is I set it equal to 2. And that way I can solve for those coordinates. Now, this isn't the best method to determine if it crosses the horizontal asymptote. Your graph and using your x-intercepts and your vertical asymptotes, that's going to give you a little bit of a better picture than going about it this way. But this is another method you could use if you want to know specifically where, just to kind of test and make sure your values are working out. So if I cross multiply, I get my equation. And then it's a simple equation from here. I end up with 9x equals 23. So x is 23 over 9. That means the intersection point would be 23 over 9, 2. All right, so that's it for solving rational functions. We'll do our last thing in the unit next class.